Hello, everybody. Sorry for the long delay in this series, um, but this is going to be the final video in the Intro to Manifolds series. So I may come back to it and, because the Intro to Manifolds was supposed to be sort of like a first chapter, sort of, and then I had planned out like 2 more chapters, but I don't think I will be continuing with the manifolds topic, because then at that point it's going to create too much of a interdependence of episodes, right? And I'd rather just make videos on different topics that are more accessible. But without further ado, this will be the final episode. So what we're considering today is vector bundles on a manifold. So the first thing, there are obviously different types of vector bundles, and the first thing we're going to be talking about is the tangent bundle. So the tangent bundle. So in a previous video, I described that for a manifold M, there is a tangent space T of M, or I guess a pointwise tangent space. So X is an element of M, means you have a tangent space at every M, right? And of course, this is just going to be a linear space which is isomorphic to, it's just a vector space of dimension equal to the dimension of M, right? Of course, since M is locally Euclidean, right, that's what a manifold is, it's locally Euclidean, then the tangent space is just a representation of that local Euclidean space. And so what we consider is all the pairs. So we consider the set of pairs X and psi, or psi, I guess is how you pronounce it, where psi is an element of the tangent space to M at the point X, right? And this is going to be what we call the tangent bundle, and we're going to denote it as L of M. Right? So essentially you just take a point in M and then consider all the possible vectors to that point. And then you consider that for each X in M, right? So X is in M, and then this vector is an element of the tangent space at that point. And so clearly the dimension of this manifold is going to be twice the dimension of M, right? Because here for X, right, the dimensionality of the first element is n, or just the dimension of M, and then since the dimension of the tangent space is also the dimension of M, you have another dimensionality of dimension of M, right? And we can show that this, I guess let me write more precisely, L of M is a manifold. Right? Of dimension 2 dim M, right? And we can show that, of course, since X and M has, so to show that this statement is true, X and M has local coordinates let's say xq, right? So x equals xq1 dot xqn, where this n is the dimension of M. And the tangent space of course, this doesn't have, you don't have local coordinates, of course, you just have global coordinates, since it's a vector space. Has coordinates given by the basis vectors, which are given by the partial derivatives with respect to the local coordinates at x, right? So this is sort of like, can write it like this, right? These are just the component. It's just a component form of the vector with respect to this basis. So n, q, right? And thus y and m, or y and L of m, has local coordinates, chords, y, which we can just write like this. We have 2n of these coordinates. And as far as transition functions go, right, because that's another important condition for our manifold, is that we have to have transition coordinates, or transition functions between local coordinates, right? The transition functions are going to be just expressed, of course, there are transition functions for the points of M, and then the transition functions for the tangent space is just going to be linear transformations given by the derivatives of the transition functions of the of x, right? So if we write that explicitly, so it's going to look like and then we get the derivatives here, p dx alpha q, alpha q, right? And so with these transition functions, you can look at okay, now you can look at the Jacobian, right? So the Jacobian is going to be the partial derivatives of the y beta p with respect to the y alpha q, right? And this is actually going to split up into a block form, and it's actually going to be a lower diagonal block form where A is simply the Jacobian on M. And the reason for this is essentially when you take along this whole, I guess this whole column, right, you're going to have let's see, taking respect to the x, taking respect to the right. So here, essentially what you're doing in the upper right quadrant is going to be something like taking derivatives of the x with respect to the vectors, which is going to give you 0. In the upper left, you're going to have derivatives of x with respect to x. In the bottom left, you're going to have essentially something like this. And then in the bottom right, you're going to have derivatives of x with respect to x, of the vector with respect to the vector, and so these are going to cancel out, and you're going to get derivatives of x with respect to x. So that's where the a is coming from, and then this expression is going to give you your h. But in the upper right quadrant, you have this 0. And the significance of this lower triagonal block form is that we can easily show that the determinant of this Jacobian is going to be equal to the determinant of a squared, which is going to be positive, right? Therefore, L of m is an oriented, or I should say orientable. Well, no, it already has in the coordinates that we've given it. It is an oriented manifold. Okay. From this tangent bundle, we can construct a subspace, or a submanifold, which is called the unit tangent bundle. Which consists of the pairs x and xi, where xi is a unit vector, right? And so this constraint is going to make L1 of m a 2n minus 1 manifold, right? So we essentially knock off a dimension from L of m because of this extra restraint. Essentially imagine, if you had a whole plane worth of stuff and then you restricted to just the unit circle, you're going from 2 dimensions to 1 dimension, right? You're restricting a dimension because of this norm condition. So that should be pretty clear. Another thing is that if you have a smooth mapping between 2 manifolds, then this induces a smooth map then L of m to L of n defined by which sends the pair x psi to f of x, and then remember, a smooth map induces a linear transformation between tangent spaces, and and so we can apply that map to Psi, and so we have an induced smooth map between the tangent bundles. There is also the cotangent bundle. Right? So I don't quite remember if I talked about the cotangent space. But essentially any vector space has a dual space, which is the space of linear functionals, or maps, from the tangent space to the scalar field, right? And that actually forms a vector space which is isomorphic in the finite case to the original vector space. So we denote this as L star of M consists of pairs x comma p, where p is a covector. And so really this is going to be p is a differential form. And cotangent bundles are very important for analyzing phase space in classical mechanics. Now suppose our manifold M has a metric G alpha beta of x, right? And a metric is just a way of pairing, basically a way of multiplying two tangent vectors. Then there is a map, a smooth map from the tangent bundle to the cotangent bundle, where we send the pair x and psi. This is sent to x and g alpha beta of x acting on psi, right? Because essentially the metric is a function which acts on two vectors, right? So if we act on one vector, then this is going to define a function which acts on one vector, and that is a covector, right? And the last definition is that of a normal bundle. So let's consider, so M is an n-dimensional Riemannian manifold. So remember, a Riemannian manifold is simply just one with a Riemannian metric, and that just means that the metric is a positive definite form, right? So it's going to be always non-negative, and it's only 0 when the two input vectors are 0. So say Riemannian manifold with n a k-dimensional submanifold. Then the normal bundle Vm of n consists of x in n, or sorry, pairs x and v, where x is an n and v is orthogonal to the tangent space at n, right? This is an n-dimensional submanifold of the tangent bundle. So I'm gonna go into more detail here because this is actually an important object. So what does this mean, right? So since we have n is a submanifold, right? The tangent space n, right, at the point x, right? If x is an n, then x is also an m, right? So this sits nicely in Tx of m, right? It's just a k-dimensional subspace of the n-dimensional vector space Txm, right? And so there are n minus k dimensions worth of this space, which is the orthogonal space, right? So this is just the space of all of the vectors which basically go outside of this tangent space. So let's take an example. Let's say we have a sphere, right? So this is S2. And of course, what I've just drawn here is an S1 submanifold, right? So if we look at it, right, S1, the tangents are going to be just these vectors which go along which are going to keep you inside of n, right? If I travel along this vector, I'm going to stay inside of this S1 submanifold. However, there's another direction. Since I'm sitting on the whole sphere, I could go in this orthogonal direction, and I'm going to leave n, right? And so that's essentially what this this normal bundle, right, is going to be all the points of this circle paired with all the vectors which are going in these up and down directions, right? That are going to travel, basically keep you straight off of the n, straight off of the submanifold. And this is n-dimensional, right? Because for x, right, you're choosing x and n, so you have k dimensions, and then you're choosing v in the tangent space, which has n minus k dimensions. And so that gives you n dimensions in total. So hopefully this little picture makes sense, and hopefully these other definitions didn't need too many examples. But yeah, so that's it for the Intro to Manifolds series. And as far as upcoming material, I'm thinking of preparing for a sort of large subject tests in mathematics, and so my university has a test bank, and so I'm thinking of going through that test bank and simply just working through the problems, explaining any definitions where I need to, and I think that might be something that is more accessible to a lot of people instead of these sort of high-level lectures. Instead, it would just be working through different proofs and problems that you might encounter in your general like algebra analysis and topology classes. I might also do some Putnam type videos. But other than that, that's it for this video, and I hopefully will be uploading more frequently in the coming winter break. So I'll see you then.